What happens in the heart of a star? We are not talking about the bright surface we see from Earth, nor the flares that streak across its atmosphere. We are referring to that hidden, inaccessible place where matter and energy face off in a titanic battle. What secrets does that core hold, where the elements that form planets, life, and ultimately ourselves are forged? This is one of the most extreme and fascinating regions of the universe, a natural laboratory where the laws of physics reach their limits and create phenomena that challenge our imagination. For centuries, stars have been objects of admiration and mystery, but if we could penetrate their layers and reach their center, we would find a radically different scene from anything we have experienced on Earth. There, the temperature exceeds millions of degrees, and pressure crushes matter to unimaginable limits. Everything that happens in that stellar heart is responsible for the light and heat that sustain the planets, and for the processes that create the essential elements for life. How is it possible that something so distant and seemingly unreachable influences our day-to-day lives so much? What really happens in that invisible center, where matter transforms and energy is born? The core of a star is much more than just a hot interior. It is a true cosmic forge, a natural reactor where atoms fuse and release colossal amounts of energy. But how do we know what happens inside, if even light cannot escape directly from that region? What clues does nature offer us to decipher the mysteries of that hidden core? The answer lies in the subtle traces, in the almost undetectable particles that reach us from the depths of the sun and from other distant stars. Every piece of data, every discovery, is a fundamental piece to understand our own origin. Exploring the center of a star is delving into the oldest history of the universe, into the process that transforms primordial hydrogen into the atoms that will form planets, oceans, and living beings. It is to question how that gigantic sphere of gas remains stable, how it withstands collapse under its own weight, and generates the energy that makes life on Earth possible. Discovering what lies in the heart of a star is, in fact, unveiling the keys that explain our existence and the ultimate fate of everything we know. What is a star really? At first glance, they seem like simple points of light in the night sky, but could it be that each one of them is much more than a distant cosmic lamp? If we ask science, the answer is fascinating. A star is a gigantic sphere of gas, primarily hydrogen and helium, that shines thanks to the nuclear reactions occurring within it. But what does that mean exactly? How can a simple cluster of gas become one of the most powerful engines in the universe? To understand it, imagine a colossal oven, so large that it could house more than 1 million planets like Earth. Inside, the temperature and pressure are so extreme that hydrogen atoms fuse to form helium, releasing an immense amount of energy in the form of light and heat. This process, known as nuclear fusion, is the true secret behind the brightness of stars. Thus, each star is, in essence, a self-sufficient energy factory, combating its own weight with the force of its own nuclear explosions. Not all stars are the same. Some, like our Sun, live relatively stable lives for billions of years. Others, much more massive, burn with such intensity that their existence is brief and dramatic, ending in spectacular explosions. Did you know that there are stars so large they could swallow hundreds of solar systems? And at the same time, there are others so small that they barely exceed the size of a giant planet. These differences in size, temperature, and brightness determine the fate and role that each star plays in the universe. But why are stars so important? Without them, the universe would be a cold and dark place, lacking the light and energy necessary for life as we know it. Moreover, stars are the forges where the heavier elements of the universe are created. All the calcium in your bones, the oxygen you breathe, and the iron in your blood once formed in the heart of a star. So, the next time you look up at the sky, remember, each star is much more than a spark in the darkness. It is a colossal creation machine, capable of transforming the universe around it. What makes a star much more than just a simple sphere of bright gas in the sky? The answer lies in its internal structure, a true masterpiece of physics, where each layer serves a vital function. Although we see them as points of light from Earth, stars are made up of several distinct layers, organized like the layers of an onion, but on colossal scales. Each of these regions has unique conditions and a specific role in stellar life. At the core, we find the nucleus, the true engine of the star. There, the temperature and pressure reach such extreme values that hydrogen atoms are forced to fuse, releasing an incredible amount of energy. Why doesn't the generated energy escape directly into space? Because it is trapped within the star and must pass through the outer layers. Just above the core lies the radiative zone, a region where energy travels slowly, as if trying to make its way through a crowd, bouncing countless times before moving outward. But the journey of energy doesn't end there. Beyond the radiative zone is the convective zone, where hot material rises and cooler material descends, creating gigantic gas currents, very much like bubbles in boiling water. What is the consequence of this movement? It accelerates the transport of energy to the surface and generates phenomena such as sunspots and coronal mass ejections in stars like the Sun. Finally, we reach the stellar atmosphere. This layer, although much less dense, is where light manages to escape and travel through the universe. The atmosphere includes regions such as the photosphere, which is the visible surface, the chromosphere, and the corona, an even more tenuous and hotter envelope. Why is the corona hotter than the surface? That remains one of the great mysteries of astrophysics. Thus, each layer of the star fulfills an essential function, and together they sustain the fascinating phenomenon we observe from Earth, the light of the stars that has traveled millions of years to reach us. What really lies at the core of a star? Much more than just a hot center, the core is the true engine of stellar life, the place where the magic happens that keeps these gigantic spheres of plasma lit. It's not an exaggeration. Everything we see in a star, from its light to its energy, depends on what happens in this tiny region relative to the star's total size. If the Sun were the size of a football stadium, its core would be barely a ball in the center. But it is there that the most explosive and fundamental reactions of the universe occur. Why is the core so special? Because it is the only place in the star where the pressure and temperature are so extreme that they can force hydrogen atoms to fuse, releasing immense amounts of energy. This central region, which usually occupies less than a quarter of the star's total radius, is the stage for nuclear fusion, the process that transforms lighter elements into heavier ones, releasing energy along the way. It's like a stellar cauldron where the laws of physics are pushed to the limit and where matter behaves in ways that on Earth we can only replicate in particle accelerators. Have you ever wondered how extreme these values are? Inside the core, temperatures can exceed 15 million degrees Celsius, and the pressure is so overwhelming that it would be like bearing the mass of millions of Earth-like planets stacked on your head. Under these conditions, protons, the positively charged particles in the nuclei of atoms, manage to overcome their natural repulsion and fuse, releasing energy in the form of light and heat. This delicate balance between the gravitational force that wants to crush the star and the energy released in the core is what keeps stars alive for billions of years. But the core is not just a fusion furnace. It is also a natural laboratory where the elements that form planets, oceans, and even our own bodies are created. Every atom of oxygen, carbon, or calcium that exists on Earth originated in the depths of some stellar core. Thus, the core of a star not only defines its fate, but also plays a key role in the history of the entire universe. Who would have thought that the heart of a star, hidden from view, would be responsible for forging the matter of which we are made? How hot can the heart of a star get? If you think the hottest fire on Earth is extreme, the stellar core takes the concept of heat and pressure to unimaginable levels. At the center of a star like the Sun, the temperature reaches about 15 million degrees Celsius. That's more than 1,000 times the temperature of the Sun's surface. To put it in perspective, if you could hold a teaspoon of material from the solar core, its energy would be enough to instantly evaporate any earthly material. And in fact, that teaspoon would weigh nearly 150 tons. But why is it necessary for the core to be so hot? The answer lies in nuclear fusion. Protons, which have a positive charge, naturally repel each other. For them to fuse and release the energy that keeps the star alive, they must be packed so tightly and move so fast that they can overcome that electrical repulsion. It's like trying to push two magnets together by the same pole. Only under truly colossal pressure and temperature would you manage to make them touch. That's why, in the stellar core, the conditions are so radical that there's nothing comparable on Earth. And what about the pressure? The star's gravity pushes all its mass toward the center, compressing the core with brutal force. This generates pressures hundreds of billions of times the atmospheric pressure of Earth. Imagine the weight of all the oceans on the planet, multiplied by millions, pressing down on every square centimeter. That pressure is essential. Without it, the atoms wouldn't be close enough for nuclear fusion to occur. These extreme conditions not only define the star's fate, but also give rise to some of the most fascinating phenomena in the universe. The enormous temperatures and pressures determine which elements are formed in the core and how much energy is released into space. Moreover, any attempt to recreate those conditions in Earth-based laboratories, even with the most advanced technology, barely scratches the surface of what happens inside a star. The extreme physics of these cores is a reminder of how powerful and mysterious the forces that govern the cosmos are. What ingredients are hidden in the very center of a star? If we could take a sample from the stellar core, what would we really find? Although stars appear to be spheres of pure light at first glance, their heart is a chemical laboratory where matter exists under extreme conditions. The chemical composition of the core is, in fact, the key to the entire process that fuels a star and determines its fate. In a star like the Sun, the dominant element in the core is hydrogen. But this is not just any ordinary hydrogen. These are atoms compressed in such a way that their nuclei, the protons, are so tightly packed that they rarely escape. Hydrogen makes up almost 3/4 of the mass of the solar core. The rest is mostly helium, which is the product of nuclear fusion. Why is there so much hydrogen? Because stars are born from primordial gas clouds, primarily composed of hydrogen, the most abundant element in the universe. However, the exact content of the core varies depending on the mass and age of the star. In young, low-mass stars, the core is almost entirely hydrogen, while as they age, helium begins to accumulate. In more massive stars, in addition to hydrogen and helium, heavier elements like carbon, nitrogen, and oxygen appear, playing a crucial role in advanced fusion cycles. And what happens in really old or extremely massive stars? Their cores can contain even heavier elements, from neon and magnesium to silicon and iron, the latter marking the limit where fusion becomes inefficient and collapse begins. Could the core of a star contain gold or lead? In reality, elements heavier than iron do not form in the core during the normal life of a star, but rather in catastrophic explosions like supernova. So, while the stellar core is a true factory of elements, there is a limit. But the variety and evolution of the elements present in the core dictate the rhythm of life and death of the star, and they determine the future chemistry of the universe, because what happens there, in that invisible center, will eventually spread throughout the cosmos and become part of new planetary systems, and even of ourselves. What makes a star shine for millions or even billions of years? Where does all that energy come from, capable of defying gravity and filling the cosmos with light? The secret lies in one of the most fascinating processes in the universe, nuclear fusion. At the heart of a star, atoms not only exist, but collide with such violence that they are forced to merge, releasing an amount of energy that is simply colossal. Nuclear fusion may sound complicated, but its essence is simple. It involves combining the nuclei of light atoms, like hydrogen, to form heavier nuclei, like helium. Why is energy released in this process? Because the mass of the helium created is slightly less than the sum of the hydrogens that produced it. That difference in mass is directly converted into energy, according to Einstein's famous equation. Energy equals mass multiplied by the speed of light squared. Although the difference in mass may seem tiny, the speed of light is so great that even a small amount of mass releases an immense amount of energy. But how is it possible for hydrogen nuclei, which naturally repel each other due to their positive charges, to come together? The key lies in the extreme conditions of the stellar core. Temperatures of millions of degrees and unimaginable pressures give particles enough speed to overcome electrical repulsion and fuse. It's like trying to bring together two repelling magnets. If you push them with enough force, they eventually come together, and when they do, they release energy. In the case of stars, that energy is what we see as light and feel as heat. In terms of efficiency, nuclear fusion is the most productive energy generation process known in nature. To put it into perspective, the energy released by fusion in the Sun every second is equivalent to the explosion of millions of hydrogen bombs at the same time. However, this process is perfectly controlled within the stellar core thanks to a delicate balance between radiation pressure and gravity. Thus, nuclear fusion is not only the engine that powers stars, but also the reason heavier elements exist in the universe and, ultimately, life itself. Did you know that the interior of a star like the Sun is the stage for a chain reaction so powerful that without it, life on Earth simply wouldn't exist? This reaction is called the proton-proton chain, and it is the fundamental process that converts hydrogen, the simplest and most abundant element in the universe, into helium, releasing an immense amount of energy in the process. But how can something as simple as two protons, the tiny particles that make up the nucleus of hydrogen, trigger such a cosmic spectacle? It all begins with an improbable encounter. Protons, both with a positive charge, should repel each other strongly, as if you were trying to bring together the north pole of two magnets. However, in the core of a star, where the temperature exceeds 15 million degrees and the pressure is enormous, protons manage to get close enough for the strong nuclear force, much more powerful than electric repulsion at tiny distances, to bind them together. This first step is so rare that each proton can expect to wait billions of years before fusing. But since there are so many, the reaction never stops. When two protons finally fuse, something magical happens. One of them transforms into a neutron, releasing a positron and a neutrino in the process. Thus, hydrogen begins to turn into deuterium, a heavier form of hydrogen. Then, that deuterium encounters another proton and forms helium-3, releasing even more energy. Finally, two helium-3 nuclei combine to create helium-4, the common helium atom, and two extra protons are expelled, ready to restart the chain. And all that effort for what? To release energy. Every time this chain reaction occurs, a small fraction of the mass of the atoms involved is converted into light and heat, thanks to Einstein's famous equation, E=mc². Although the percentage of mass converted is tiny, the number of reactions that occur every second within a star is so gigantic that the energy released sustains the brightness and life of the star for billions of years. Thus, the proton-proton chain is not just a nuclear engine. It is the essential recipe for a star like the Sun to shine. But why is it called a chain? Because it is a sequence of steps, each linked to the previous one, and each link is crucial for the process to work. If one fails, energy production stops. This delicate balance makes the proton-proton chain one of the most efficient and astonishing natural wonders of the cosmos. And although the precise details of the reaction challenge human intuition, the result is simple, straightforward, and spectacular. Light and energy, being born every second in the hearts of stars. Did you know that in the core of the most massive stars, a nuclear reaction occurs that is even more complex than simple hydrogen fusion? This process is called the CNO cycle, and it is one of the main engines that keeps the largest stars in the universe shining. But how exactly does this mechanism work, and what makes it so special compared to other stellar fusion processes? In the CNO cycle, the true protagonists are not just protons, but also three well-known elements: carbon, nitrogen, and oxygen. These act as catalysts, meaning they help transform hydrogen into helium without being consumed in the process. It's as if they were chefs in a stellar kitchen, facilitating the recipe for nuclear fusion over and over again, allowing energy to continue being generated efficiently. Why do the most massive stars prefer this method? Because the CNO cycle requires much higher temperatures than those found in stars like our Sun. Above 15 million degrees, the CNO cycle activates and outperforms other fusion pathways in efficiency. The chain begins with a carbon nucleus capturing a proton, transforming into nitrogen through several steps, and releasing energy in the form of gamma rays and subatomic particles called positrons and neutrinos. The process continues with transformations between nitrogen and oxygen until finally, the original carbon nucleus is regenerated and a helium nucleus is released. Thus, the cycle repeats infinitely, as long as there is enough hydrogen and the extreme conditions of temperature and pressure are maintained. And what are the consequences of this for the universe? The CNO cycle not only fuels the luminosity of giant stars, but also plays a key role in the creation and distribution of heavy chemical elements. Through this cycle, stars enrich their cores with carbon, nitrogen, and oxygen, and when they die, they release these elements into space, sowing the raw materials for new worlds and, potentially, for life itself. Surprisingly, the carbon and oxygen atoms that make up your body may have been cooked in the heart of some gigantic star billions of years ago, thanks to the magic of the CNO cycle. What does this reveal about the inner workings of a star? The CNO cycle demonstrates that nature finds different paths to achieve the same result, keeping the star alive and generating the energy that illuminates galaxies. It reminds us that although all stars may seem similar at first glance, very different nuclear games may be happening inside them, depending on their mass and temperature. How many other secret processes are hidden in the hearts of stars, waiting to be discovered? The CNO cycle is just one of the many hidden wonders in the universe. What happens to the energy generated in the center of a star? How does that energy escape from such a dense and extreme place to finally reach space? The answer is a fascinating story of resistance and patience, where every photon born in the core must navigate a true labyrinth before seeing the light of day, literally. In the core, nuclear fusion releases an enormous amount of energy in the form of gamma radiation, a light millions of times more energetic than what we perceive on the solar surface. But that energy does not travel directly outward. The interior of the star is so dense that each photon, in trying to move forward, collides time and again with particles of matter. It's as if a crowd were trying to exit a stadium, but each person had to change direction thousands of times, bouncing among the other attendees before reaching the exit. This process, known as radiative diffusion, can take hundreds of thousands, even millions of years for the energy of a single photon to escape from the core to the surface. But is it only light that carries the energy outward? No. In the outer layers of the stellar interior, especially in the convective zone, another crucial mechanism comes into play: convection. There, the hot gas rises because it is less dense, while the cold gas descends, creating enormous bubbles that transport energy, almost like boiling water in a pot. Thus, the movement of stellar material helps to extract the energy that the core has produced, accelerating the final journey of that heat to the surface. Once the energy manages to reach the surface of the star, it is finally released into space, primarily as visible light and other forms of radiation. This energy is what bathes the planets, fuels life, and allows us to exist. every ray of sunlight that we feel on Earth is the culmination of a journey that began in the heart of a star, overcoming almost unimaginable obstacles. Who would have thought that the light warming us today could have spent millions of years bouncing inside a gigantic sphere of plasma before reaching our faces? Moreover, not all the energy generated in the core travels as light. A significant part escapes in the form of neutrinos, ghostly particles that pass through matter almost without interacting. While photons remain trapped for eons, neutrinos escape almost instantaneously, carrying with them direct information from the core. Thus, the release of energy from the center of a star is not only a slow and complex process, but also the source of phenomena that connect us to the depths of the cosmos. What happens in the core of a star? How do we know what occurs millions of kilometers away, in a place where matter is so compressed and hot that no telescope can look inside? The answer lies in almost ghostly messengers called neutrinos. These tiny particles, virtually massless and electrically neutral, travel through space and matter as if nothing could stop them. If a star were an impregnable fortress, neutrinos would be the perfect spies. They enter and exit undetected, carrying with them invaluable information. Every second, trillions of neutrinos pass through our bodies without us knowing. They are generated in enormous quantities during nuclear fusion reactions in the stellar core. And while photons, the light we eventually see, can take thousands or even millions of years to escape from inside a star, neutrinos do so almost instantaneously. It's as if in a marathon from the center of the star to outer space. Neutrinos are runners that pass through walls, while photons get trapped in an endless maze. But why are neutrinos so important for science? Detecting them is extremely difficult, but when we succeed, we gain a direct window into the heart of stars. Neutrinos hardly ever interact with matter. That's why scientists must build enormous detectors buried under mountains or deep within the Earth, shielded from other particles. It's like trying to hear the whisper of a leaf in the middle of a storm. It takes a very sensitive ear and a very quiet place. Thanks to the detection of neutrinos coming from the Sun and other stars, we have confirmed that nuclear fusion really occurs in their cores, just as theories predict. Without neutrinos, much of what we know about stellar interiors would be mere conjecture. These invisible messengers are the irrefutable proof of the most extreme and mysterious processes happening in the universe. And they remind us that, although the cosmos holds many secrets, there are always clever ways to uncover them. What keeps a star shining for millions or even billions of years without collapsing or exploding immediately? The answer lies in a kind of cosmic tug-of-war between two fundamental forces, gravity and radiation pressure. On one hand, gravity acts like a gigantic hug, pulling all the material toward the center of the star. If gravity were the only player, the star would crush itself in a matter of seconds. But there is an equally powerful force opposing it: the internal pressure generated by nuclear fusion. Where does this pressure that defies gravity come from? Every second in the stellar core, millions of fusion reactions convert hydrogen atoms into helium. This process releases a colossal amount of energy in the form of photons, particles of light. The energy of these photons exerts an outward pressure known as radiation pressure. It's as if the inside of the star is being inflated from within, pushing the material outward and preventing it from collapsing under its own weight. But how is the balance achieved between these two titanic forces? The key lies in what is called hydrostatic equilibrium. If nuclear fusion generates too much energy, radiation pressure increases and the star tends to expand, cooling its core and slowing down fusion. If the energy is insufficient, gravity takes control, compressing the core and causing the temperature and fusion rate to rise. Thus, the star self-regulates, remaining stable for most of its life. It's a constant and subtle adjustment, like a cosmic scale that never stops moving, but rarely goes entirely out of balance. Can this battle last forever? The answer is no. Over time, the nuclear fuel runs out and the delicate balance is broken. But as long as the star has hydrogen to fuse, radiation pressure and gravity remain in a cosmic dance, sustaining the star's brightness and shape. This balance is so precise that a small variation could change the fate of an entire solar system. The next time you look at a star, remember that what keeps its light burning is a constant struggle between invisible forces that shape the universe. What triggers the birth of a star? The story begins in the dark, cold heart of a gigantic cloud of gas and dust known as a nebula. These nebulae, at first glance, are nothing more than enormous opaque patches in space, but within them lie all the necessary ingredients to create a star. Why does the gas cluster in certain regions and not simply disperse? The answer lies in gravity. Small fluctuations in density within the cloud cause some areas to be slightly denser than others. This difference, though minimal, initiates a domino effect. Matter begins to attract more matter, and the entire cloud starts to fragment into more compact cores. Is the process of star formation quick? Quite the opposite. It can take millions of years as gravity continues to compress the gas and dust, squeezing them tighter and tighter. As the cloud contracts, the temperature and pressure at its center increase dramatically. Imagine the air inside a bicycle pump. When you compress it, it heats up. This is what happens inside these protostars, but on colossal scales. When the central temperature reaches about 10 million degrees, the miracle occurs. Hydrogen atoms begin to fuse, releasing an enormous amount of energy. That is the signal that a star has been born. What determines whether the star will be giant or tiny? It all depends on the amount of material available in the original nebula. If the cloud is massive, gravity allows for the formation of a large star, capable of burning its fuel at a rapid pace and shining brightly, albeit for a shorter time. If the cloud is small, the resulting star will be modest, like red dwarfs, which can burn for trillions of years. It's like making a campfire. The more firewood you have, the bigger and brighter the fire will be, but it will also burn faster. And what happens around the newly born star? The leftover material can form rotating disks of gas and dust, from which planets, asteroids, and comets arise. Thus, the birth of a star is also the beginning of a planetary system, as if the cosmic recipe included, in addition to the main star, the ingredients for entire worlds. Each star, in a way, is the beating heart of a small universe. Hydrostatic equilibrium is the delicate balance that keeps a star alive and stable for most of its existence. But what forces are really battling in the heart of a star? On one side, gravity acts relentlessly, trying to compress all the matter toward the center. On the other, the internal pressure generated by nuclear fusion pushes forcefully outward. This rivalry is so fundamental that any small imbalance can change the fate of a star. Why is it so difficult to achieve this state of equilibrium? Because the conditions in the core are extreme. Temperatures of millions of degrees and unimaginable pressures that challenge even the most advanced laboratories on Earth. If you've ever wondered how a star can last millions or even billions of years without collapsing or exploding suddenly, the answer lies in this balance. Think of it as a constant battle, like two teams pulling on a rope in a tug of war. If gravity wins, the star compresses and increases the temperature and pressure in the core until nuclear fusion accelerates and generates more internal pressure. If, on the other hand, the internal pressure is greater than gravity, the star expands and fusion slows down. Hydrostatic equilibrium is that exact point where both forces balance out, allowing the star to maintain its shape and size for a long time. But how does a star know when to stop? It doesn't really know. Its behavior is a direct consequence of physical laws. If the star begins to collapse, the compression increases the temperature and pressure in the core, accelerating nuclear fusion. As a result, more energy is generated and the internal pressure rises, halting the collapse. If the star expands, the temperature and pressure drop, fusion decreases, and gravity regains control, slowing the expansion. This automatic adjustment is so precise that, For most of its life, a star remains in a perfectly balanced dance. Can this equilibrium last forever? No. Hydrostatic equilibrium depends on having fuel available for nuclear fusion in the core. As hydrogen runs out, the internal pressure decreases and gravity starts to win the game, triggering new stages in the life of the star. However, as long as it lasts, this balance is the secret that allows stars as stable and luminous as the Sun to exist. Ultimately, the path to hydrostatic equilibrium is a constant, invisible, but decisive struggle that defines not only the life of a star, but also the fate of the planets and the life that may orbit around it. How different can the cores of stars be? The answer is much more than we could imagine. Not all stars are the same, and their core, that burning heart where everything happens, changes radically depending on its mass, age, and composition. If we thought of stars as cosmic factories, some would be small and efficient, while others would be huge and explosive, each with its own rhythm and its own recipe for manufacturing the elements of the universe. The lighter stars, known as red dwarfs, have relatively cool and dense cores compared to larger stars. What does this mean? That inside them, nuclear reactions occur very slowly, allowing these stars to live billions of years without exhausting their fuel. Their cores are like slow cookers. They consume hydrogen slowly, maintain a temperature of a few million degrees, and never fuse elements heavier than helium. That's why, although they are the most common stars in the universe, they are also the most discreet and long-lived. In contrast, the core of a massive star is a true furnace of high pressure and temperature, exceeding hundreds of millions of degrees. Here, it's not enough to fuse hydrogen. As soon as it runs out, the star initiates a cascade of increasingly complex fusions, helium into carbon, carbon into oxygen, and so on, until reaching iron. But why iron? Because it is the last element that can be formed while releasing energy. From there, the star can no longer sustain itself, and its fate becomes complicated. These stars live fast and die young, in spectacular explosions that scatter new elements throughout space. And what about white dwarfs and red giants? In the case of white dwarfs, the core is practically all that remains, an ultra-dense sphere of carbon and oxygen, where matter is so compressed that a teaspoon would weigh tons. In red giants, on the other hand, the core becomes small and extremely dense compared to the colossal size of the star. Here, hydrogen has already been exhausted, and what remains is a series of fusion layers, like the layers of an onion, each one hotter and more active than the previous one. In summary, the core of a star is like its fingerprint. No core is the same as another. Its composition, temperature, and behavior depend on factors such as mass, age, and environment. From small dwarfs that burn their fuel slowly to titans that blaze with fury and vanish in cataclysmic explosions, the stellar core reveals the astonishing diversity of processes that keep the universe alive and in constant evolution. Why is the Sun so fundamental to understanding the heart of all stars? Because it is the only star whose core, although unreachable, we can study with an unimaginable level of detail compared to any other. The Sun, at 150 million kilometers from Earth, acts as our cosmic laboratory, allowing us to observe phenomena occurring in the interiors of other distant stars. But here, with precise and constant data. How is it possible that we know so much about what happens in its core if we have never been there? The answer lies in the combination of measurements, theoretical physics, and the interpretation of particles that travel directly from its interior. At the center of the Sun, the temperature reaches approximately 15 million degrees Celsius, a figure so colossal that it defies imagination. What does this mean in practice? If we could take a single grain of sand from the solar core and bring it to Earth, its heat would be enough to instantly kill any living being in its proximity. But it's not just heat. The pressure in that core is equivalent to millions of times the Earth's atmospheric pressure. Under these extreme conditions, hydrogen atoms fuse to form helium, releasing a colossal amount of energy. This fusion process is the true engine of the Sun, and the reason why light and heat reach our planet every day. How do we know this is the case? One of the keys lies in neutrinos, ghostly particles that pass through matter almost without interacting. Every second, trillions of neutrinos from the solar core are passing through your body right now completely unnoticed. Detecting solar neutrinos has been one of the greatest challenges in physics, but their discovery confirmed that nuclear fusion occurs exactly as predicted by theory. It's like receiving a direct message from the very heart of the sun, proof that our equations and models are not only elegant, but also correct. Has the sun always functioned the same way? No. Thanks to the study of its oscillations, a kind of solar seismology, we have been able to explore its interior indirectly. Vibrations on the solar surface reveal information about the deeper layers, just as seismologists study the Earth's interior from earthquakes. This data has confirmed that the sun's core is stable, but it changes slowly over time. As it converts hydrogen into helium, the core becomes denser and hotter. Consequently, the sun shines today with more intensity than it did billions of years ago, and it will continue to increase its brightness throughout its life. Although there are stars much larger, hotter, or cooler than the sun, none are as close or as accessible for continuous observation. Therefore, every advance in the study of the solar core is, in reality, an advance in the understanding of all the stars in the universe. The sun is not only the source of our light and heat, it is a direct window into the intimate workings of the nuclear furnaces that populate the galaxy. Have you ever wondered what happens between the burning core of a star and its brilliant surface? There lies a fascinating region known as the radiative zone, a kind of cosmic waiting room where the energy generated at the center of the star begins a surprisingly slow journey outward. But why does energy, which travels at the speed of light, take so long to cross this place? The answer lies in the unique and extreme conditions of stellar matter. In the radiative zone, the energy produced in the core does not move freely. Instead, it travels through a process called radiative transport. Imagine light as a traveler in a crowded train station. Every time it tries to move forward, it collides with a throng of particles, especially free electrons and atomic nuclei, which absorb it and re-emit it in another direction. This endless bump and bounce causes photons, which are the particles of light, to take thousands, even millions of years to exit the radiative zone and make their way to the stellar surface. Thus, while light travels incredibly fast in a vacuum, inside a star, its path resembles that of a person trying to leave a very crowded party. The temperature in this region remains extremely high, although lower than in the core. It can reach several million degrees, enough to keep the matter completely ionized, meaning there are no complete atoms, just nuclei and electrons floating freely. This soup of particles constitutes a dense plasma in which photons are trapped and must bounce again and again. Why does this phenomenon occur? Because the density is so high that the average distance a photon travels before being absorbed or scattered, called the mean free path, can be just a few millimeters, even though the radiative zone is hundreds of thousands of kilometers thick. And what role does this zone play in the functioning of the star? It acts as a natural regulator, carefully dosing the energy that comes out of the core before it reaches the outer layers. If the energy were released too quickly, the star would become unstable. But thanks to the radiative zone, energy is released gradually, allowing the star to maintain its structure and shine steadily for millions or billions of years. Without this traffic jam of photons, stars could not exist as we know them. In summary, the radiative zone is an invisible yet fundamental barrier where energy makes its way slowly, as if trapped in an eternal maze. Every photon that manages to escape this region has survived a true odyssey, and only after this tortuous journey can it continue its path to the outer layers, where the amazing process of bringing light and heat to the universe will continue. What happens to the energy generated in the core of a star after it passes through the radiative zone? It reaches a fascinating region, the convective zone. Here, the physics changes completely. Instead of energy traveling slowly as photons bouncing between atoms, heat is transported in a much more efficient and dynamic way, almost as if the star were boiling from the inside. Why does this change occur? Because in this zone, matter is so opaque that photons can no longer advance easily. So, the star resorts to a more direct method. Enormous bubbles of hot plasma rise, while the cooler material descends, mixing like currents in a pot of hot soup. Have you ever wondered why the surface of the sun seems to be in constant boiling? The answer lies in the convective zone. The hot material rises to the outer layers, releasing energy into space, and then descends as it cools, in a cycle that repeats millions of times per second. This process is called convection, and it is the same phenomenon you can observe when water boils in a pot. The hot liquid rises and the cooler one sinks. In the star, however, the scales are colossal, and each bubble can be larger than an entire land continent. But what lies just above the convective zone? There we find the visible surface, known as the photosphere. Although we often think of a star's surface as a sharp boundary, it is actually a thin layer of just a few hundred kilometers thick compared to the total size of the star. From the photosphere is where light finally escapes into space, reaching our eyes after a journey of millions of years from the core. That light we perceive is nothing more than the energy released by the processes occurring deep within the star, transformed and filtered through all its layers. The interaction between the convective zone and the surface has surprising consequences. For example, the so-called convection cells generate bright and dark patterns on the solar surface, known as granules. Each of these granules is a bubble of hot plasma rising, surrounded by cooler bands that descend. Additionally, intense magnetic fields originate in the convective zone, responsible for spectacular phenomena such as sunspots and solar flares. Thus, convection not only explains how energy reaches the surface, but also many of the most impressive and mysterious characteristics of stars. Who would have thought that, at the heart of it all, is simply heat rising and falling, like in a gigantic cosmic pot? What happens in the heart of a star when hydrogen, its main fuel, runs out? The answer is as dramatic as it is fascinating. Hydrogen is the lightest and most abundant element in the universe, and within the stellar core, it is the essential raw material for nuclear fusion. But the star cannot fuse hydrogen forever. Eventually, the reserves begin to dwindle, and the internal balance, which seemed unbreakable, starts to wobble. Does this mean the end of the star? Not exactly. In fact, this is when one of nature's most spectacular transformations begins. When hydrogen is depleted in the core, the nuclear fusion that converts it into helium stops in that central region. Without the energy produced by fusion, the internal pressure that kept gravity at bay decreases. It's as if suddenly the main engine of a gigantic machine shuts down. Gravity, which has always been present, seizes the opportunity and begins to compress the core with relentless force. Meanwhile, the outer layers of the star, which no longer have the same internal support, also respond to this change. What triggers this new stage? The increase in temperature and pressure in the core as it contracts. Helium, which has been accumulating after millions of years of fusion, is now the protagonist. As the core compresses, temperatures can reach extreme values, enough to ignite a new series of nuclear reactions, helium fusion. But not all stars achieve this immediately. In stars with a mass similar to the Sun, the onset of helium fusion is so sudden and violent that it is called a helium flash, a kind of silent explosion within the core that completely restructures the stellar interior. However, in much more massive stars, the process is more gradual. Why is it different? Because the conditions of pressure and temperature vary greatly depending on stellar mass, and that determines the fate of each star. As the core transforms, the outer layers of the star react by expanding impressively, turning the star into a red giant. The surface cools, luminosity increases, and the size multiplies many times over. It's as if the star, having run out of its main fuel, transitions from a compact ball of energy to an inflated colossus in space. During this stage, fusion shifts to a layer surrounding the core, where hydrogen is still available. Thus, the star continues to shine, but its internal structure has changed forever. How far can this process go? The answer depends on the amount of mass the star has from its birth. Some will be able to fuse helium and then even heavier elements, while others, less massive, will be unable to initiate new fusions, wilting into much smaller and cooler objects. The truth is that the depletion of hydrogen marks a turning point, the beginning of a metamorphosis that will decide the star's final fate. The death of hydrogen in the core is not an immediate sentence, but the spark that triggers one of the most extraordinary stages of stellar life. What happens when a star exhausts the hydrogen in its core? This is where a fascinating new stage of its life begins: helium fusion. But why is this process so special? Unlike hydrogen, helium requires much more extreme temperatures and pressures to fuse. Only when the star's core reaches around 100 million degrees can helium nuclei, made up of 2 protons and 2 neutrons, get close enough to join together. It's like trying to bring together 2 extremely powerful magnets, both with the same pole. The repulsive force is enormous, and only under extreme conditions can they fuse. So, what exactly happens during helium fusion? The main process is called triple alpha. Sounds curious, right? It's named that because essentially 3 helium nuclei, also known as alpha particles, combine to form a carbon nucleus. First, 2 helium nuclei fuse to create beryllium. However, this beryllium is very unstable, and if it doesn't quickly encounter another helium, it disintegrates in a flash. But if a third helium particle arrives in time, a stable carbon nucleus is formed. This step is crucial because, thanks to it, heavier elements essential for life as we know it are produced. And what impact does helium fusion have on the star? The sudden ignition of helium fusion releases a huge amount of energy in a very short time, an event known as a helium flash, especially in low or intermediate mass stars. This outburst is not visible from the outside, but it completely changes the internal structure of the star. The core expands, the pressure stabilizes, and the star enters a new phase of equilibrium. The result can be surprising. The star swells and may become an even larger red giant. Its surface cools and takes on a more reddish hue. Did you know that this process is crucial for the universe? Without helium fusion, carbon and other heavier elements simply wouldn't exist in significant amounts. Every carbon atom in your body was once forged in the heart of a star during helium fusion. Thus, this process acts as a kind of cosmic factory, building the fundamental building blocks of life. But helium fusion is not the end. In even more massive stars, the core will continue to fuse increasingly heavier elements, taking stellar alchemy to even more astonishing and extreme levels. How far can a star go in the manufacturing of the elements that make up our universe? The answer is surprising and largely defines the very origin of everything around us. In the heart of a star, not only is light and heat produced, there, under extreme conditions of pressure and temperature, a true cosmic factory of heavy elements takes place. But how does a star manage to transform simple hydrogen atoms into much more complex materials like carbon, oxygen, or even gold? It all begins when the hydrogen in the core runs out and the star must seek new sources of energy. Then, the core contracts and the temperature rises even further, allowing helium nuclei to fuse to form carbon. This process, known as the triple alpha process, is fundamental. 3 helium nuclei come together to create a carbon atom, an essential component for life as we know it. But the story doesn't end there. If the star is massive enough, it can continue fusing carbon, oxygen, neon, magnesium, and other elements, advancing in a sort of ladder of increasingly demanding nuclear reactions. Did you know that the heaviest elements beyond iron cannot be formed efficiently solely through fusion in the stellar core? When the star reaches the point where the core is primarily composed of iron, it faces a physical limit. Fusing iron does not release energy. In fact, it consumes it. So, how do we end up with gold, platinum, or uranium on Earth? The key lies in explosive and extreme events, such as supernova. In the final moments of the lives of the most massive stars, the energy released in a supernova is so colossal that it can forge even heavier elements through rapid neutron capture in processes known as rapid nucleosynthesis, or the R process. Think about it for a moment. Every calcium atom in your bones, the oxygen you breathe, the iron in your blood, all those elements were born in the forge of a star, or in the violent death of one. Stars, then, are much more than mere points of light. They are cosmic alchemists, responsible for the fundamental ingredients for the existence of planets, oceans, and life. Thus, the mystery of the stellar core lies not only in its functioning, but in the way it transforms the simplest into the most complex, in an unceasing cycle that connects every corner of the universe. Who would have imagined that our own story was written, atom by atom, in the burning heart of the stars? What happens in the heart of the most massive stars in the universe? What unimaginable processes turn these giants into true cosmic forges? The core of a massive star is an extreme laboratory, where matter and energy meet under conditions that do not exist anywhere else known. There, gravity is so intense that the material is compressed to densities millions of times greater than those we experience on Earth. But that's not enough. The temperature can exceed hundreds of millions of degrees, enough to unleash nuclear reactions far more complex than those that fuel stars like our Sun. In these cores, fusion does not stop at hydrogen. Why? Because the pressure and heat are so immense that atoms continue to fuse in a chain of stages, forming increasingly heavier elements. When hydrogen runs out, the core begins to fuse helium into carbon and oxygen. And what happens next? If the star is massive enough, fusion progresses. Carbon turns into neon, neon into magnesium and oxygen, and so on, as if the core were an onion, with layers of heavier elements stacked on top of each other. This process continues until iron is formed, the final point of stellar fusion. Why iron? Because fusing iron atoms does not release energy. It consumes it, and that completely changes the star's fate. Are you surprised to think that all the elements that make up your body, the Earth, and even the gold in jewelry come from these stellar furnaces? It is in the cores of massive stars where almost all the heavy elements of the universe are born. Each stage of fusion produces new atomic nuclei, which will be scattered across the cosmos when the star dies. The physics behind these processes is so intense that, in the final moments, the core can collapse in a fraction of a second, releasing energy equivalent to the explosion of millions of suns in a supernova. It is that event that disperses the newly created elements, seeding the universe with the basic ingredients for new stars, planets, and eventually, life. But beyond the creation of elements, the core of a massive star is a stage where physics reaches its limits. Nuclear forces, extreme gravity, and incredible temperatures combine to challenge our understanding of matter. What exactly happens in those final moments, when the pressure can no longer support the weight of the accumulated iron? The core collapses, and depending on the mass, it can give rise to one of the most exotic and mysterious objects, a neutron star, or even a black hole. Thus, the cores of massive stars are not only the forges where the periodic table is created, but also the portals to the most extreme phenomena of the known universe. What happens when gravity tries to crush the core of a star beyond its limits? Is there any force capable of resisting such pressure, even when nuclear fusion can no longer help? This is where one of the most fascinating and counterintuitive concepts in physics comes into play: quantum degeneracy. Unlike conventional forces like gas pressure or radiation, quantum degeneracy is a phenomenon that arises directly from the strange and unbreakable rules of the quantum world. To understand it, one must remember a fundamental law of nature, the Pauli exclusion principle. This principle tells us that two particles called fermions, such as electrons or neutrons, cannot occupy exactly the same quantum state at the same time. Why is this important at the heart of a star? Imagine trying to fit many people into a small elevator. At first, they can squeeze in, but there comes a point where they simply cannot fit anymore, no matter how much you push. Something similar happens in the stellar core when gravity compresses electrons or neutrons so much that there is no available space in the lowest energy levels. Forced to occupy higher and higher states, they generate a pressure that does not depend on temperature, but on pure quantum mechanics. Can this invisible pressure stop the collapse of a star? Yes, and in fact, it is the reason why objects like white dwarfs and neutron stars exist. When a star exhausts its nuclear fuel and gravity tries to compress its core to the extreme, the electron degeneracy pressure can halt the collapse. This is how white dwarfs are born. Incredibly dense cores, roughly the size of Earth, but with a mass comparable to that of the Sun. However, if the mass of the core is even greater, the electron degeneracy pressure is no longer sufficient, and electrons merge with protons, forming neutrons. Then, neutron degeneracy pressure takes over, leading to neutron stars, even more compact and extreme objects. Is there a limit to degeneracy pressure? Surprisingly, yes. If the mass of the core continues to grow, even neutron degeneracy cannot stop gravitational collapse. In that case, matter is compressed beyond any known limit, and a black hole forms, a region of space where not even light can escape. Thus, quantum degeneracy marks a cosmic boundary, determining the ultimate fate of stellar cores. Without this phenomenon, the universe would be very different. White dwarfs and neutron stars would not exist, and the life cycle of massive stars would end in a much less interesting way. In short, the role of quantum degeneracy in the cores of stars is that of an invisible guardian. It is a force we cannot see or touch, but it defines the limits of matter under the most extreme conditions of the cosmos. Thanks to it, we know that the universe is not only governed by gravity and energy, but also by the strange and powerful laws of quantum mechanics, which at the heart of a star can mean the difference between survival or total disappearance. What happens when a star reaches the end of its life and can no longer sustain itself? The fate of its core becomes a true cosmic battle between titanic forces. For millions, or even billions of years, nuclear fusion has been the engine that keeps the star in balance, generating enough pressure to counteract gravity. But when the fuel runs out, this delicate balance is broken. What happens next? Gravity, which had been contained until then, takes absolute control and causes the core to collapse inward toward its own center. This collapse is not a simple shrinking, it is an implosion of unimaginable proportions. In a matter of seconds, the core can compress from the size of Earth to just a few kilometers in diameter. The outer layers of the star, suddenly deprived of the core's support, fall inward at dizzying speeds. But upon colliding with the collapsed core, they bounce back and are violently expelled into space in a colossal explosion, the supernova. How powerful is a supernova? In a single instant, it can release more energy than our sun will emit throughout its entire existence. Supernovas are much more than cosmic fireworks. They are true factories of heavy elements. In the extreme conditions of these explosions, atoms like gold, uranium, or platinum can form and be scattered throughout the universe. Every heavy atom on our planet, every ring of gold, every cell in our body with iron, has its origin in the violent death of a star. Why is this so relevant? Because without supernovas, complex chemistry and life itself, as we know it, simply would not exist. After the explosion, the final fate of the core depends on its mass. If it is large enough, it can continue collapsing until it overcomes any resistance, creating a black hole, a region where even light cannot escape. If the mass is smaller, the result may be a neutron star, an object so dense that a teaspoon of its material would weigh millions of tons. In both cases, the collapse and explosion of a star mark not only the end of a stellar cycle, but the beginning of new chapters in the evolution of the universe. Thus, the end of a star becomes the origin of new worlds and possibilities. What happens when the core of a massive star reaches the end of its life? Is it possible for matter to be compressed to almost unimaginable limits? When a star with enough mass exhausts its nuclear fuel, its core faces a cosmic crossroads. Gravity, freed from the pressure of fusion, takes absolute control and crushes the core inward with colossal force. But how does matter respond to such crushing? This is where two of the most extreme objects in the universe appear: neutron stars and black holes. A neutron star is the result of a controlled collapse, if such a dramatic event can be called controlled. The star's core, compressed by gravity, reaches such extreme densities that protons and electrons fuse to form neutrons. The result? A sphere just about 20 kilometers in diameter, but with more mass than the Sun. To put it in perspective, a teaspoon of material from a neutron star would weigh hundreds of millions of tons. It's like concentrating the weight of a mountain into the space of a sugar cube. But how does something so dense hold itself up without collapsing completely? The key lies in the so-called neutron degeneracy pressure, a quantum principle that prevents neutrons from being compressed indefinitely. But what happens if the core is even more massive, exceeding the limit of what quantum pressure can support? In that case, gravity has no opponent. The collapse continues unabated, and matter concentrates into a point of infinite density, called a singularity. This is how a black hole is born. The extraordinary thing about a black hole is its event horizon, an invisible boundary beyond which nothing, not even light, can escape. How can one imagine something like that? It's as if gravity has dug a well so deep that you could never climb out of it, no matter how fast you ran or how high you jumped. Black holes are the great devourers of the cosmos, and their core, if it can be called that, completely defies our known laws of physics. Both destinies, neutron star and black hole, represent the most extreme final states of matter after stellar death. But how do we know they exist if we cannot see them directly? In the case of neutron stars, their magnetic fields and rapid rotations can produce beams of radiation known as pulsars, which we detect from Earth as periodic signals. And black holes, although invisible, reveal their presence by the way they warp space-time and affect nearby matter, such as gas disks spinning at dizzying speeds and emitting enormous amounts of energy before crossing the event horizon. Thus, the core of a star can become one of the most extreme and mysterious natural laboratories that exist, where the laws of physics are truly put to the test. What happens when a star has exhausted its nuclear fuel and can no longer fuse elements? The answer is surprising. A white dwarf is born. But what is its core like? What secrets does this stellar remnant, which was once the beating heart of a star like our Sun, hold? In the core of a white dwarf, we find one of the most extreme states of matter in the universe. Although the word dwarf may sound modest, we are actually talking about an object with a mass comparable to that of the Sun, but compressed into a volume similar to that of the Earth. Imagine taking all the matter from our king star and squeezing it until it fits into a sphere the size of our planet. What happens to the atoms under such conditions? They get crushed until the electrons are so close together that they generate a quantum pressure called electron degeneracy pressure. It is not the pressure generated by heat, but by the rules of quantum mechanics, which prevent two electrons from occupying the same state. It's like a room full of people where no one can occupy the same chair. When all the chairs are taken, no one else can sit down, and that resists gravitational collapse. What is the core of a white dwarf made of? Predominantly carbon and oxygen, the residual products of nuclear fusion that occurred during the star's active life. However, there are variants composed of helium or heavier elements like neon and magnesium, depending on the original mass of the progenitor star. Despite its incredible density, about 200,000 times that of water, the core of a white dwarf does not possess active nuclear fusion. It is a turned-off furnace, glowing only from the residual heat trapped inside. How is it possible for such a dense core not to collapse under its own weight? The key lies in electron degeneracy pressure. Unlike normal stars, where the thermal pressure of hot gas keeps gravity at bay, in the white dwarf, it is quantum physics that holds the entire structure together. If we try to add more mass to it, the pressure from the electrons reaches its limit, and the star collapses further, transforming into a neutron star or a black hole if it exceeds a certain critical threshold, known as the Chandrasekhar limit, about 1.4 times the solar mass. Can the core of a white dwarf change over time? Yes, but extremely slowly. Without nuclear fusion, the only possible evolution is gradual cooling. Over billions of years, the core loses heat and energy, becoming colder and darker, until it turns into a hypothetical black dwarf, an object that, for now, only exists in theory because the universe is not old enough to have produced one. Thus, the core of a white dwarf is the silent testimony of stellar death, a place where matter is so compressed that it defies intuition, governed by strange and fascinating quantum laws, and which can endure cooling slowly for longer than life has existed on Earth. What happens in the core of a red giant? It's easy to think that an aging star is simply a larger, cooler version of its youth, but the reality is much more fascinating. At the heart of a red giant, the core is a chaotic and extreme environment, where transformations occur that will decide the star's ultimate fate. Why does a star swell to become a red giant? The answer lies precisely in what happens within its core. When the hydrogen in the core runs out, the star loses its main source of energy. Does that mean the star simply shuts down? Not at all. Gravity, relentless, begins to compress the core, making it denser and hotter. This compression triggers an unexpected reaction. Around the inert helium core, a layer forms where hydrogen continues to fuse. This fusion shell generates such colossal pressure that the outer layers of the star expand and cool, transforming it into a red giant. And what exactly is that core now? It is a helium core, extremely compact and hot, where pressure and temperature reach values that defy imagination. If the Sun could become a red giant, its core would be so dense that a teaspoon of that material would weigh more than 100,000 tons. But despite that heat and pressure, helium still cannot fuse. It needs even higher temperatures, on the order of 100 million degrees, for helium fusion into carbon and oxygen to occur. When those conditions are finally reached, what astronomers call the helium flash happens, a sudden and gigantic release of energy that completely changes the internal behavior of the star. In more massive stars, the cycle can continue. Once helium fuses, the core can ignite new fusion phases, creating increasingly heavier elements like carbon and oxygen. But in less massive stars, like our Sun, the process stops there. The core of a red giant, then, is the final battleground of a mature star, a natural laboratory where the elements that will later enrich the universe are forged. Isn't it amazing to think that the carbon atoms in your body, or the oxygen you breathe, were born in cores like this, in the fiery twilight of giant stars? Thus, the core of a red giant is not just a hot, compressed remnant. It is the engine of a cosmic transformation. As its outer layers expand and slowly shed into space, the core continues to change, setting the stage for the final stages of stellar life. This region, invisible to our eyes but fundamental to the evolution of the cosmos, is the true factory of the essential elements for life and galaxies. How many more secrets will the core of a red giant hold before revealing its final act? Did you know that the core of a star can be the site of some of the most powerful magnetic fields in the universe? But how is it possible for magnetism to exist in such an extreme and chaotic place as the stellar heart? To understand this, we must remember that deep within the core, matter is neither solid nor liquid, but a dense and hot plasma primarily made up of protons and electrons in constant motion. And where there are charged particles moving, magnetic fields are inevitably generated. In fact, this phenomenon is so universal that it also occurs on Earth, but on a much smaller scale. How does this magnetism affect the star? Contrary to what we might think, magnetic fields are not only present on the visible surface of stars, where they cause storms and sunspots. In reality, the core can also harbor powerful internal magnetic fields, which can sometimes be millions of times more intense than those of our planet. These fields can influence the way energy is transported, altering the dynamics of particles and, in some cases, modifying the rate of nuclear fusion. It's as if the core is crossed by invisible threads that, when tightened or relaxed, affect the balance and stability of the star. What happens when the magnetism in the core becomes especially intense? In extreme cases, such as in neutron stars, the remnants of massive dead stars, magnetic fields can reach such colossal values that they deform matter and generate exotic phenomena like magnetars. These objects possess magnetic fields capable of stripping electrons from atoms at unimaginable distances. Although in living stars the fields are usually less intense, their influence can explain phenomena such as variability in luminosity or the appearance of regular magnetic cycles, similar to solar cycles, but much more energetic. Can we directly measure the magnetism in the core of a star? Not directly, but scientists have developed ingenious methods to infer its presence. For example, certain oscillations observed on the stellar surface can reveal the existence of deep magnetic fields. Additionally, the way energy waves propagate, or even the characteristics of the emitted light, can carry the imprint of internal magnetism. In summary, although the magnetism in the stellar core is invisible to our eyes, its effects are so profound that they can transform the life and fate of a star. Without these fields, the universe would be a much more monotonous and predictable place. What if I told you that stars, just like musical instruments, can vibrate and emit notes that reveal their deepest secrets? Although we cannot hear these vibrations as a melody, astrophysicists have learned to interpret stellar oscillations, just as an experienced musician deciphers the notes of a score. But why do stars vibrate? And how can that tell us something about their core, a place we will never be able to travel to? Stars are not completely rigid spheres. They are enormous balls of hot gas subjected to colossal forces. Inside, pressure and gravity waves can travel and bounce, generating small expansions and contractions that ripple throughout the stellar body. These movements are so subtle that, in the case of the Sun, the surface can shift just a few meters, while the star itself measures over 1 million kilometers in diameter. How can scientists detect something so tiny? The key lies in analyzing the tiny changes in brightness and movement on the stellar surface, which act as echoes of what is happening inside. Stellar seismology, or astroseismology, is the science that studies these vibrations. It works similarly to terrestrial seismology, where geologists analyze earthquakes to uncover the Earth's internal structure. In the case of stars, astrophysicists observe how certain acoustic waves, called pressure modes, travel through the plasma and become trapped inside the star, vibrating like sound in a bell. Depending on the density, temperature, and composition of the core, the frequency and intensity of these oscillations change, allowing scientists to hear the secret heartbeat of the star and deduce details about its internal structure. Can this technique really reveal what is at the heart of a star? The answer is astonishingly yes. Thanks to the study of oscillations, we know, for example, that the Sun's core rotates faster than its outer layers and that its interior is more homogeneous than previously thought. In other stars, asteroseismology has allowed us to estimate their age, size, and even the amount of heavy elements present in their core. All of this without needing to travel there, just by carefully listening to the vibrations that reach us, sometimes from hundreds or thousands of light years away. Perhaps the greatest wonder of stellar seismology is that it shows us how ingenious science can be in deciphering the mysteries of the universe. Who would imagine that by analyzing the silent song of a star, we could reconstruct its history, its composition, and its ultimate fate? Stellar oscillations are much more than mere movements. They are encoded messages, a hidden language that, once deciphered, allows us to peek into the very heart of these cosmic giants. How is it possible to know what happens at the center of a star if we can never travel there? It's like trying to discover what's inside a sealed safe without having the combination. Astrophysics, however, has developed ingenious ways to spy on the stellar core without ever opening it. What are the clues that allow us to reconstruct its composition, temperature, and activity? The key lies in interpreting indirect signals, like cosmic detectives following tiny traces in the vast universe. One of the most surprising tools is stellar seismology, a technique that studies the vibrations and oscillations of a star's surface. Each vibration is like the echo of a drum. Depending on what is inside, the sound changes. Similarly, the seismic waves traveling through the star reveal information about its various internal layers, including the core. How are these vibrations detected? By analyzing variations in the star's brightness, as each heartbeat modifies the light that reaches us. Thus, we can deduce the density, size, and even the rotation of the core, almost as if we were listening to the heart of a living being light years away. But vibrations are not our only clue. Particles called neutrinos, nearly impossible to catch, are direct messengers from the core. Generated in deep nuclear reactions, neutrinos manage to escape from the star's interior and travel to Earth with hardly any interaction with matter. Detecting neutrinos is a monumental challenge. Trillions pass through our bodies every second without leaving a trace. However, underground observatories, buried under mountains or ice, have managed to capture some of these elusive visitors. Why is this so important? Because the presence and quantity of neutrinos confirm that nuclear fusion really occurs in the stellar heart, validating what our theories predict. Another piece of evidence comes from the star's own light. To the naked eye, it appears as a continuous emission, but when dispersed into a spectrum, dark and bright lines appear, like a cosmic barcode. These spectral lines tell us what elements are present in the star's atmosphere, but they can also reveal information about internal processes. For example, the presence of certain isotopes or the variation in brightness over time can indicate changes originating in the core, such as the onset of new fusion stages. Even the life and death cycle of stars, observed in stellar populations of different ages, helps reconstruct the history of what happens in their hearts. Together, science has developed a kind of cosmic X-rays. By interpreting vibrations, neutrinos, and light patterns, we can deduce what happens at the center of stars without needing to open them or physically approach them. It is an extraordinary example of how human intelligence can unravel the deepest secrets of the cosmos, using only the clues that the universe allows us to see from afar. Thus, although the stellar core remains hidden from plain sight, its traces are etched in the light and particles that travel to us, allowing us to reconstruct the history of those cosmic forges millions of light years away. How is it possible to know what happens in the core of a star when we can't even see its surface in detail? The answer lies in a powerful and fascinating tool, computational simulation. But what does it really mean to simulate the core of a star? It's like building a virtual laboratory where the laws of physics are the rules of the game, and extreme conditions, temperatures of millions of degrees, crushing densities, and colossal forces, can be reproduced without limits. In that digital environment, astrophysicists can experiment, adjust parameters, and observe how the heart of a star evolves over timescales that, in reality, would span millions or even billions of years. Is it as simple as entering some numbers into a program and waiting for magical results? Not by a long shot. Simulating the core of a star is one of the greatest challenges of modern astrophysics. An overwhelming number of variables must be taken into account: chemical composition, nuclear fusion rates, energy flows, plasma movements, and even the effects of relativity. Each of these variables can completely change the star's fate. Computational models must be so precise that any small error could lead to incorrect conclusions about a star's life and death. Why are these simulations so crucial? Thanks to them, we can answer questions that were once impossible. How long will the sun last before exhausting its hydrogen? What exactly happens when a massive star collapses into a supernova? At what point does the fusion of heavier elements begin? Moreover, simulations allow us to test hypotheses that are impossible to verify in an Earth-based laboratory. For example, how does matter behave when the pressure is so high that atoms are crushed almost to the point of disappearing? Only computational models can explore that forbidden territory. And how do we verify that these virtual models reflect reality? This is where comparison with real observations comes into play. The light we receive from stars, the neutrinos detected on Earth, and the stellar vibrations observed by specialized telescopes. When the predictions of the simulations match the observed data, astrophysicists can trust that they have deciphered, at least in part, the secrets of the stellar core. Thus, computational simulation becomes a kind of intellectual spaceship, capable of traveling to the very heart of stars and revealing what we will never be able to see with our own eyes. What if I told you that there are stars that pulse, not with a heart of flesh and blood, but with their own burning core? Variable stars are one of the most fascinating mysteries of the cosmos. At first glance, they seem to twinkle, but in reality, their brightness changes regularly or irregularly for reasons that lead us straight to the center of their being. What causes a star to change its brightness as if it were breathing? The answer lies, largely, in what happens in its core. When we observe a variable star, what we see is the result of internal processes that affect its structure and vital rhythm. In some stars, the core experiences periodic pulsations due to temporary imbalances between the pressure generated by nuclear fusion and the force of gravity. It's as if the star is trying to find a perfect balance, but never quite achieves it. Why do they fail to remain stable? Often, it all begins with small fluctuations in the energy released in the core, which propagate outward and cause the star to literally expand and contract, altering its luminosity. But not all variable stars pulse for the same reasons. Some, like the famous Cepheids, function almost like cosmic clocks. In their case, the mystery lies in a thin layer of ionized helium within the star. When the star compresses, this layer becomes more opaque, trapping heat and causing the star to expand. As it expands, the layer becomes transparent, heat escapes, and the star contracts. This surprisingly predictable cycle directly connects the behavior of the core with the changes we observe from Earth. Did you know that thanks to Cepheids we can measure distances in the universe? Their regularity has been key to discovering the true size of our galaxy and the expansion of the cosmos. On the other hand, there are variable stars whose behavior is much less orderly. Some exhibit sudden bursts of brightness or abrupt drops, and in many of these cases, the secret still lies in the core, but also in the surrounding layers. Sometimes, the outer layers of the star absorb and release energy in unexpected ways, or the core changes its fusion pattern, sending shockwaves outward. Even in binary systems, one star can steal material from its companion, altering what happens in its own core and triggering unpredictable variations in its brightness. How far does our knowledge of variable stars extend? Although we have deciphered many of their secrets, each new observation reveals surprising details about how the stellar core can affect the visible universe. Variable stars are natural laboratories, where extreme physics manifests on colossal scales. They remain one of the best clues to understanding what happens in the hidden heart of stars, and therefore, in the very foundations of the universe. Who would have thought that the simple twinkling of a star could hide so much information about the deepest mysteries of the cosmos? What happens when two stars come so close that their destinies become intertwined forever? The so-called double stars, or binary systems, are not just a cosmic rarity. In fact, most stars in our galaxy are born in pairs. But what happens at the heart of these systems when the distance between them shortens so much that they begin to share matter, and even, in extreme cases, their very cores? When one star orbits another closely enough, gravity starts to play a nearly mischievous role. Imagine two dancers spinning so closely that their dresses intertwine, allowing one to steal part of the other's outfit. Similarly, in some binary systems, the outer envelope of one star begins to flow toward its companion, a process known as mass transfer. But can this exchange reach all the way to the very core? In extraordinary cases, the answer is yes. During so-called contact or stellar merger phases, the boundaries between both cores can blur, resulting in a shared core, a true fusion of stellar hearts. This phenomenon leads to a series of fascinating effects. For example, mass transfer can rejuvenate an old star, making it shine with renewed intensity, while the other weakens and ages prematurely. Did you know that some of the most massive stars known in the universe are actually the result of the union of two smaller stars? By sharing their cores, these merged stars can trigger titanic explosions like especially bright supernovae, or even end up forming unusually massive black holes. The inevitable question is, what signals allow us to discover these shared cores? Astrophysicists rely on clues such as variations in luminosity, changes in rotation speed, and even extremely energetic X-ray emissions. These details betray the violent exchanges of matter and energy within binary systems. Ultimately, the study of double stars and their shared cores not only reveals a cosmic choreography of great beauty, but also helps us understand how the most exotic and extreme objects in the universe are formed. What really happens inside the core of a star as it ages? Why is the heart of a young star so different from that of an old star? To understand these differences, let's think of the stellar core as the engine of a car. When it's new, it runs efficiently, but over time and with use, its functioning and internal characteristics change. Thus, the core of a young star and that of an old star are similar only in name, but in reality, they are completely different physical scenarios. In the core of a young star, hydrogen is the undisputed protagonist. It is the raw material that, through nuclear fusion, turns into helium and releases an enormous amount of energy. This process occurs under conditions of temperature and pressure so extreme that it's hard to imagine. Tens of millions of degrees and pressures that would crush anything we know on Earth. But what happens when the star starts burning through its fuel? Does it suddenly stop shining? No. What occurs is much more fascinating. The core begins a transformation, as if a new story were being born within the star. As the star ages and the hydrogen in its core is depleted, helium begins to accumulate at the center. This is where the real change begins. It can no longer continue the usual fusion, so the star must adapt. How does it achieve this? The core contracts, further increasing the temperature and pressure, until it can initiate the fusion of helium into heavier elements such as carbon and oxygen. In more massive stars, this chain of fusions can continue, forming increasingly complex elements, while in less massive stars, the process halts earlier, resulting in cores rich in helium or carbon. The core of an old star is much denser, more compact, and hotter, almost as if the star is squeezing out every last drop of internal energy. The difference between a young core and an old one is not just a matter of age, but of composition and destiny. While the young core is primarily hydrogen and in stable equilibrium, the aged core is composed of heavier elements and faces instabilities. These instabilities can lead to pulsations, changes in brightness, and in extreme cases, set the stage for colossal explosions like supernova. Why is this important? Because the elements forged in the old cores of stars are literally the building blocks that form planets, life, and ultimately, everything we know. Thus, the evolution of the stellar core is a journey of transformation and cosmic recycling. Each stage is crucial. The youth of the core defines the stability and brightness of the star, while the old age of that core determines its final destiny and contributes to the chemistry of the universe. Isn't it amazing to think that by looking at a bright star, we are witnessing in real time the story of its heart, from its explosive youth to its old age filled with secrets and possibilities. What does the core of a star have to do with the evolution of entire galaxies? It may seem surprising, but the fate of billions of stars and how they change over time largely determines the fate of an entire galaxy. If the universe were a city, stars would be its factories. In their cores, they transform simple materials into increasingly complex elements, and through their life cycles, those elements are released and recycled, shaping and giving life to the galaxy. The stellar core is the true cosmic engine of galactic evolution. There, nuclear fusion creates elements like carbon, oxygen, or iron, essential for the chemistry of planets, the emergence of atmospheres, and even life itself. When a massive star reaches the end of its existence, its core can collapse and trigger a supernova. Why is this so important? Because at that moment, the elements manufactured over millions of years are ejected into space, enriching the interstellar gas and allowing new generations of stars and planets to form with more complex materials. Thus, each stellar core is a kind of galactic alchemist that transforms the simple universe into a rich and diverse one. But how does this affect the entire galaxy? Massive stars and their cores act almost like gigantic switches, controlling the rate of star formation. When they explode, their shockwaves can trigger the birth of new stars in nearby clouds, or conversely, sweep away gas and slow formation in certain regions. Moreover, the cores of the heaviest stars contribute to the creation of black holes and neutron stars, objects that can alter galactic dynamics, influence the formation of star clusters, and even affect the structure of spiral arms. Not only that, the chemical composition of an entire galaxy is the direct result of the work done in the cores of millions of stars over billions of years. When astronomers observe distant galaxies and analyze the light they emit, they can deduce how many generations of stars have lived and died within them, all thanks to the chemical fingerprints left by stellar cores. Thus, the burning heart of each star is not only responsible for its own fate, but also gradually writes the evolutionary history of the galaxy to which it belongs. What relationship exists between the blazing core of a star and daily life on Earth? The answer is, quite literally, in every ray of light that reaches us from the sun. But how is it possible that the solar core, millions of kilometers away, has such a direct effect on our planet? The key lies in the energy generated there, deep within the sun, and in the extraordinary journey that energy takes to reach us. In the solar core, temperatures reach 15 million degrees, and the pressure is so intense that hydrogen atoms fuse, releasing a colossal amount of energy. This energy does not come from nowhere. It is the result of nuclear fusion, the same process that powers all the stars in the universe. But what does this mean for Earth? Without nuclear fusion in the sun's core, our planet would be a frozen, dark world, incapable of supporting any life. All the energy that allows for the existence of plants, animals, and human beings ultimately comes from that stellar engine. Have you ever stopped to think about how long it takes for energy to travel from the solar core to us? Surprisingly, the photons generated at the center of the sun can take hundreds of thousands of years to pass through the dense inner layers. It's as if the energy is trapped in an endless maze, colliding over and over again before finding an exit. Once it manages to escape the solar surface, that light travels through space in just a little over 8 minutes before bathing the Earth. Thus, the energy that fuels photosynthesis, climate, oceans, and even the water cycle originated from events that occurred long before humanity existed. And what importance does this have for life on Earth? Absolutely everything. Solar energy is the primary source that drives the great gears of the planet. Without it, ecosystems would collapse, winds would cease to blow, and oceans would freeze. Even the energy we use when turning on a lamp, eating a fruit, or breathing oxygen is somehow linked to the nuclear fusion of the solar core. If you ever wonder why life exists on Earth, The answer lies, in large part, in the blazing heart of the sun, in that small core where matter transforms into light and heat for the entire solar system. Thus, the connection between the core of a star and our planet is much more intimate than it seems. Every dawn, every breeze, and every form of life is a testament to a chain of processes that begins 150 million kilometers away, at the center of a sphere of plasma. Understanding this connection not only inspires admiration, but also reminds us how fragile and extraordinary life is under the light of a star. How big can a star be? When we talk about hypermassive stars, we delve into a realm where physics stretches almost to the limits allowed by the laws of the universe. These stars, with masses exceeding more than 100 times that of the Sun, challenge everything we usually imagine about the size and power of these cosmic objects. But what really happens in the core of such a colossal star? How is it possible for it to stay intact and not collapse under its own weight? The core of a hypermassive star is a true energy cauldron, where temperatures can reach hundreds of millions of degrees Celsius, and the pressure is so intense that a teaspoon of that material would weigh millions of tons. To put it in perspective, if the core of a star like this could be placed on Earth, it would crush anything in its path and would, in fact, pass through the planet as if it were butter. The density and energy released every second are so extreme that matter behaves in ways that are almost incomprehensible from our everyday experience. What are these cosmic beasts made of? Mainly hydrogen and helium, but unlike more modest stars, hypermassive ones fuse elements at a dizzying speed. The core can traverse the entire chain of nuclear reactions, from hydrogen fusion to the creation of much heavier elements, such as oxygen, magnesium, or even iron, in a surprisingly short time. Instead of living billions of years, these stars can consume themselves in just a few million. It's as if they burn their fuel with the veracity of a race car engine, leaving an unmistakable chemical footprint in the cosmos. But then, what happens when such a star reaches the end of its life? This is where nature shows its most spectacular side. The core can no longer withstand the pressure, gravity wins the battle, and a catastrophic collapse occurs. In a matter of seconds, the star can explode in a supernova that releases more energy than our Sun will emit in its entire existence. In some extreme cases, the remaining core can form a stellar mass black hole, a region of space where even light cannot escape. Thus, hypermassive stars are not only laboratories of extreme physics, but also creators of the most enigmatic and powerful objects in the universe. Is there a limit to the size of a star? The answer is yes. The laws of physics impose a boundary known as the Eddington limit, beyond which radiation pressure would expel excess gas and prevent the star from continuing to grow. However, in distant galaxies, astronomers have found candidates for stars with up to 300 times solar mass, like the famous R136A1. These colossal forges of heavy elements remind us that, in the universe, there is always room for the extraordinary, and that the larger a star is, the more fleeting and explosive its life is. What if there were such strange stars that challenged everything we think we know about the cosmos? Beyond traditional stars, there are hypotheses about objects so exotic they seem straight out of a science fiction novel. Could the core of a star be made up of something completely different from the atoms we know? Astrophysicists have wondered whether, under extreme conditions, matter can reorganize itself into forms that we can't even see on Earth. One of the most fascinating concepts is that of quark stars. What are quarks? They are elementary particles, even smaller than protons and neutrons, the basic components of atomic nuclei. Under unimaginable pressure and temperature conditions, such as those reached when a massive star collapses, protons and neutrons could disintegrate, releasing quarks that form a kind of ultra-dense soup. Could there be a star with a core made exclusively of this quark soup? Although we have not observed one directly, theoretical models suggest they could be even denser than neutron stars, to the point that a teaspoon of their material would weigh more than a mountain. But the universe doesn't stop there. The existence of even more extravagant star cores has been proposed, such as strange matter cores. What does this mean? Instead of being made up of the most common quarks, they could contain a mixture of strange quarks, a type of particle that normally doesn't survive for long. On Earth, strange quarks disintegrate almost immediately, but in the heart of an exotic star, the pressure could hold them together, creating a completely new and unknown form of matter. Could it be that some of the densest stars in the universe are, in fact, natural laboratories of particle physics, producing matter that we could never recreate in our accelerators? And the proposals don't end there. There are theories that even discuss the possibility of cores with boson condensates, particles that obey quantum rules different from those of ordinary quarks and electrons, or stars that contain cores made of dark matter, that mysterious substance that makes up most of the universe's mass. Could a star have at its core a substance that doesn't even interact with light? While this sounds like pure speculation, every time astronomers find a star with unusual properties, the question arises whether we are facing one of these exotic objects. What significance do these strange cores have? Beyond scientific curiosity, understanding them could reveal secrets about the fundamental laws of the universe. If we manage to detect signals from these exotic cores, we could open the door to new physics, beyond what is known. For now, the study of exotic stars reminds us that, even in a universe we think we understand, there is always room for the unexpected and the extraordinary. What really happens at the very center of a star? Although science has made tremendous strides in understanding stellar processes, there are still fascinating questions that keep astrophysicists awake at night. Do we know in detail how matter behaves under such extreme pressures and temperatures? Current theories predict the behavior of plasma in the core, but when conditions exceed what we can recreate in terrestrial laboratories, uncertainties arise. For example, are there phases of matter that we still do not know, hidden in those hostile environments? Another major mystery revolves around the exact mechanisms of energy transport and the possible unexpected fluctuations within the stellar interior. Could there be unknown processes that alter the efficiency with which energy generated by fusion escapes to the surface? Even neutrinos, those almost ghostly particles that pass through matter without interacting, continue to pose mysteries. Do we really understand all the ways they are produced and behave in the hearts of stars? Models predict certain quantities, but measurements sometimes reveal slight discrepancies that are hard to explain. The most massive stars take this enigma even further. In their cores, matter can reach such high densities that the known laws of physics are put to the test. What happens exactly when the pressure is so intense that atomic nuclei disintegrate into even more fundamental particles? Could exotic matter form, like a quark soup, or even states of matter that are still unknown? Quantum physics and general relativity intertwine in these extreme environments, and even the most advanced equations fail to describe everything with certainty. Finally, there is a fundamental mystery. How do internal magnetic fields and stellar oscillations really affect the behavior of the core? While vibrations and magnetic variations have been detected, the way they influence the structure and evolution of stars remains an open frontier. Are there still unidentified mechanisms that could trigger sudden changes or unexpected explosions? Each star is, in essence, a natural laboratory of extreme physics. And although we have unveiled many of its secrets, the center of a star still holds enigmas that challenge our imagination and our most solid theories. What drives a star to shine for millions or even billions of years? The answer lies in its core, that hidden heart where matter and energy intertwine in an unimaginable dance. If you've ever wondered why the sun doesn't go out overnight, the explanation is hidden in the extreme processes occurring deep within its being. The stellar core is not just a hot place, it is a true natural laboratory where the normal rules of matter are pushed to the limit, and where atoms transform to give rise to the light and heat that make life possible on planets like Earth. Is it possible that in the future we could replicate the power of the stellar core here on Earth. Scientists have been trying for decades to mimic the nuclear fusion that occurs in the hearts of stars, dreaming of a clean and inexhaustible energy source. However, the conditions that exist inside a star, temperatures of millions of degrees and colossal pressures, challenge our current technology. Each advance in understanding these processes brings us a little closer to that goal, but the challenge remains monumental. The core of a star is still, for now, a reminder of how far we are from mastering the deepest secrets of nature. What does the core of a star tell us about our own origin? Much more than we could imagine. In that cosmic furnace, the heaviest elements are forged, from the carbon in our bodies to the gold in our jewelry. Every atom of oxygen we breathe and every particle of calcium in our bones ultimately originated in the core of some star that existed long before the sun. Thus, understanding the heart of stars is also understanding our own history. We are, literally, stardust. Is there anything left to discover at the center of a star? The answer is a resounding yes. Despite the enormous advances in astrophysics, there are still unresolved mysteries. How does matter behave in such exotic states? Are there forms of matter still unknown, like quark cores? What exactly happens in the final moments before a star collapses? The stellar core, that enigma wrapped in plasma and gravity, continues to invite us to explore and dream, reminding us that, in the universe, even the most hidden places can be the key to understanding it all.